So now let's summarise what we've done in this section on modular arithmetic. We began by saying that two numbers, a and b, are equivalent modulo n, or congruent modulo n, or even just equal modulo n, if they have the same remainders after dividing by n, or equivalently, if a minus b is divisible by n. And then we saw that when we're adding or subtracting two numbers, or multiplying two numbers, then the result modulo n depends only on the original numbers themselves modulo n. So if a1 and a2 are equal modulo n, and b1 and b2 are equal modulo n, then a1 plus b1 and a2 plus b2 are equal to one another modulo n, and the same for subtraction and the same for multiplication. And then we showed an algorithm for quickly computing a raised to the power k modulo m. And this is going to be particularly important in RSA cryptography, in which case, in particular, when we're doing decryption, and the number k, so we're looking at a to the k modulo m, k may be 300 or 600 digits long, and we certainly don't want to do 300 or 600 multiplications, even if we just took the remainder modulo n at each stage. And the idea behind the algorithm was to write the power k as a sum of powers of 2. And then we computed a to these powers of 2. So a squared, a to the power 4, to the 8, a to the 16, a to the 32, a to the 64. And in fact, if we're looking at 300 digit k, we'd only need to do 900 of these roughly, which is nothing compared with the size of a 300 digit number. So that's actually ends up being a very quick computation. Then, because we saw that addition and multiplication modulo m only depend on the numbers a and b themselves modulo n, then if we restrict to numbers lying between 0 and n minus 1, where we're taking modulo n, we looked at the modulus tables, and this here is just a shorthand, it's just a way of denoting addition modulo n, and likewise for multiplication modulo n. And we saw that the mod 7 and mod 8 tables, respectively, were typical of the case of a prime and of a non-prime, respectively. Then we gave the multiplicative inverses theorem, and if we're working modulo n and we take a number a between 1 and n minus 1, then provided the greatest common divisor of n and a is 1, that means n and a have no common factors, which will always be the case if n itself is prime, because if n is prime and a lies in this range, then certainly a cannot divide n, cannot divide a prime. So then in that case, and more generally in this case where the greatest common divisor of a and n is equal to 1, then by the extended Euclidean algorithm we saw previously that there must be s and t such that sa plus tn is equal to 1, and we also saw the converse, that if there are s and t such that sa plus tn is equal to 1, then the greatest common divisor is indeed 1. In other words, n and a have no common factors. And that was quite easy to prove, because if we have any divisor of a and n, then let's call it d, then d must divide this number, and so therefore it divides 1, and the only way a positive integer can divide 1 is if it's equal to 1 itself. So that means the greatest common divisor is in fact 1. We then saw that under those circumstances that a has a unique multiplicative inverse modulo n. And in fact we also showed that these three were equivalent in the sense that if a has a unique multiplicative inverse modulo n, or indeed if a just has a multiplicative inverse modulo n, in which case it will be unique, then these here are all true. And we also showed the multiples of a, 2a, 3a, up to n minus 1 times a, taken modulo n, they're all different, and they are just a permutation of the numbers 1, 2, up to n minus 1. So we had that all of these conditions here are equivalent. Once we know any one of them, the other three follow. And you can track that from what we've already proved. And it's also an interesting exercise to show each one of these implications directly. In other words, to show, for example, that this here, the third one, is equivalent to this one here, and that this one implies this one, and conversely this implies this, to try and show it directly without going through any of the other equivalences. So some interesting exercises there. And finally, we proved Fermat's little theorem. Fermat's little theorem says that if P is prime and P does not divide A, then A to the power P minus 1 is congruent to 1 modulo P. Now, because we're working modulo P, then we can assume that A must lie in the range 1 up to P minus 1. And the proof now of that actually was fairly quick using this result here, because if we put n equals P into here, and we're taking, as we saw, as we just explained, A to be less than or equal to P minus 1, then from here we must have that we multiply all these numbers and take the remainder modulo n. It'll be the same as multiplying all these numbers. So that gives us that this is congruent to this, is equal to this modulo P, and this here is just A to the P minus 1 times P minus 1 factorial, and this is P minus 1 factorial, and then we justified dividing, in this case, through by P minus 1 factorial and getting this result. So that's just an overview or a summary of what we showed in this section.